Hello, friends. Welcome back. We are starting our 7th unit on thermodynamics, and we're going to start this lesson by doing what, depending on how much you remember from regular chemistry, is somewhat of a review. We're going to be talking about what heat really is in terms of energy, and the process of calorimetry, how it works, and do a bunch of practice problems. So, first of all, thermochemistry or thermodynamics is just the study of heat absorbed or released during chemical and physical changes. So, how much heat is released, how much heat is absorbed through the process. So, a couple definitions, and right here for just a few minutes, we're going to kind of combine chemistry and physics a little bit. So, if you've taken AP Physics, you're going to recognize a few things, but then we're going to quickly switch to just chemistry. So, energy is the capacity to supply heat or to do work. Work is causing matter to move against an opposing force. So it's how much force is over a distance. So there are two types of energy. We have potential energy, which is energy an object has because of its relative position, composition, or condition. So in chemistry, we're going to be thinking about it more in terms of its composition or its condition. So the type of, the state of matter or what the actual identity of the chemical substance is. But if you want to think of potential energy in terms of position, you could think of it like the water at the top of the dam is the potential energy, and then as the water flows, it has kinetic energy, which is the energy an object has due to motion. So something that is fundamental to all thermochemistry is the law of conservation of energy, which states energy cannot be created nor destroyed. It can only change form. So we are never, ever, ever going to have energy come from nowhere, and it's never going to disappear, okay? So when one substance is converted into another, there is an association of a conversion of one form of energy into another. So heat energy to light energy, electrical, chemical, mechanical. So an example is we all pump gas into our cars, right? And that gas is what helps our cars run. So the chemical energy that is stored in the gasoline goes through a combustion reaction, and that energy is then converted into mechanical energy, which makes your car run. So a way we can think about this equation-wise is that heat lost must equal heat absorbed or heat gain. That always has to ring true. Heat lost must equal heat gain. So what is heat? So heat essentially is a transfer of thermal energy between two objects of different temperatures that are in contact. So energy flows from an object with higher energy to an object with lower energy until they're at the same temperature. So this flow is going to continue to happen until they're at equilibrium. So for example, if your hands are ever really cold and you put them on the back of your neck, your neck is like a really warm part of your body. You're kind of going to feel the temperature difference, and then heat is going to transfer from your neck to your hands until they're in the same temperature. Same idea as if I sit my coffee out all morning, like I always do. Eventually, my coffee's room temperature because heat has escaped from my coffee into the atmosphere until they're the same temperature. The equation for heat is Q equals mc delta T. So this is heat. We're going to go over these units in a second, but that's typically in joules. M is mass, which is, of course, in grams. C is specific heat. Again, we're going to review what these units are in a moment, but it's in joules per gram degrees Celsius. And then, of course, delta T is just in degrees Celsius. That's temperature change. Now, what delta means is change, if you're not aware of that, or change in. So technically, delta T is the final temperature minus the initial temperature. So one time in chemistry, I had a student who was like, but what do I plug in for the triangle? And I was like, nothing. Delta T is just change in temperature. It's one number. It's one value. Okay. So thermal energy specifically is any energy that's coming from heat. So that's different than chemical energy or mechanical energy or so on and so forth. So what is temperature then? Well, temperature is the average kinetic energy. It's a quantitative measurement of hot and cold. So high kinetic energy is a high temperature. Low kinetic energy is a low temperature. So if you look at this graph, we're looking at the number of molecules with certain amounts of energy. So at a colder sample, we have much lower energy on average than in a warmer sample. So temperature is just a measure of average kinetic energy. So again, I told you we were going to talk about these units. Heat is typically measured in calorie or joule. Calorie is the one we're used to seeing on like food. The amount of energy required to raise 1 gram of water by 1 degree Celsius. So again, that's what we see in food because it tells us how many calories, basically how much heat it takes to burn, how much energy it's going to take to burn that amount of food. So that's the calorie. A joule is defined as the amount of energy used when a force of 1 Newton moves an object 1 meter. Now, it's kind of strange that it's talking about movement, newtons, and all that stuff. You don't really need to worry about that. We use joule most often, pretty much exclusively in this class. The conversions, 1 calorie is 4.184 joules, but again, we mostly use joules. A couple terms that are important that you should already know. Something is endothermic when heat is absorbed. So if it takes heat from the surroundings, like in this picture, then the surroundings are going to feel cold. If something is exothermic, heat is released. And so if it's releasing heat, like in this picture on the right, then it is going to cause the surrounding temperature to increase. Okay, that next part of our Q equals mc delta T. C is specific heat, but first I want to talk about heat capacity. They're very similar, but slightly different. So heat capacity is the quantity of heat an object absorbs or releases when it experiences a temperature change of 1 degree Celsius. So it's heat over the change in temperature. So this is going to depend on the type and the amount of the substance. So it is an extensive property, meaning this much water is going to have a higher heat capacity than this much water, simply because it's larger. There's more of it, it can absorb more water. Now, specific heat capacity is the quantity of heat required to raise the temperature of 1 gram of a substance by 1 degree Celsius. So now we take into account the mass. So it only depends on the kind of substance. It's an intensive property. This much water and this much water would have the same specific heat because they all would take 4.18 joules to raise 1 gram by 1 degree Celsius. Doesn't matter how much of it you have. So this is kind of showing that again. We have 2 cast iron pans. The larger one is going to have a higher heat capacity than the smaller one just because it's more material there. But they would have the same specific heat. They would both have whatever the specific heat of iron is. Something here to point out, metals have typically low specific heats. That means they heat up quickly, but they also cool down quickly. If you ever think about if you've taken a baking sheet out of the oven and you sit it on the counter, just a couple minutes later, it's pretty cool to the touch, or at least it's touchable. Alcohol, like hand sanitizer, very low specific heat. Immediately, it evaporates almost, like it's gone from your hands in seconds. Water, really high specific heat. It takes a while for it to evaporate. It's going to take a while to boil it. That all comes down to specific heat. So I'm going to do a couple of practice problems with this calorimetry. So if you want to pause and try it yourself, go for it. If you want to watch the first one and then pause and try the second one. For both of them, we're going to be using this Q equals mc delta T. And so we look at these problems. It says a flask containing 800 grams of water is heated. The temperature goes from 21 to 85, and the specific heat is 4.18 for water. So we're solving for heat here. I'm going to plug in my mass. I'm going to plug in my specific heat. And then I'm going to plug in my change of temperature, which is 85 minus 21, which is 64. Now, real quickly, I'm going to show you how the specific heat units make sense. See here how when we multiply grams times grams and degrees Celsius times degrees Celsius, we're left with joules, which is what heat is in, so that's what we need. When we calculate this, we get 214,016 joules. Something you will see a lot in this unit is a lot of times heat is converted into kilojoules. And that's just because we sometimes end up with really, really large quantities of heat. And so kilojoules just make them smaller, more manageable numbers. Obviously, they're the same amount. We're just expressing them in a different unit. So if you do need to go joules to kilojoules, remember you're going to divide by 1,000 because kilo means 1,000. So there's 1,000 joules in 1 kilojoule. All right, I'm going to do the next one. We have 500 grams of iron, increases temperature from 25 to 250, and its specific heat is 0.451. So Q equals, the mass is 500, specific heat is 0.451, and the change in temperature is 225 degrees Celsius. When I do that math, I get 50,738, and if I want, I can express that as 507 kilojoules. So nothing too complicated with those calculations. Kind of really just plugging and chugging. You got 4 variables. You're going to be missing one. You're going to solve for the one you're missing. So now we're going to talk about calorimetry. Okay, and so calorimetry is a way that we can measure heat, or really calculate heat from measurements, because we cannot measure heat directly. We don't have a heatometer, right? But we can calculate temperature change, and then we can calculate, or we can measure temperature change, and we can calculate the heat. So calorimetry is measuring amounts of heat transferred to or from a substance during a chemical or physical change. So something we need to keep in mind, a system is whatever is undergoing the physical chemical change, and then the surroundings are other components of the measuring device. So when we talk about something transfers heat to its surroundings, we're saying that the system itself transfers heat from the system into the surrounding. So a calorimeter is the device used to do calorimetry. It's used to measure the amount of heat involved. So we use the mass if we're looking at an object, the specific heat, and the temperature change in order to calculate heat. Because like I said, we can't measure heat directly. We don't have a heatometer, right? So we calculate it with this equation. So a lot of times, especially in chemistry classes, we just use a very simple coffee cup calorimeter. You have 2 styrofoam coffee cups, one nested inside the other one, and that's going to insulate pretty well. We have a thermometer down in there, but they aren't the most accurate, but they work pretty well for, a chemistry lab. So in simple calorimetry, like if you did do this in regular chemistry, you probably talked about like using different metals, maybe finding the specific heat of the metal, or if you know the specific heat, you can determine the heat transfer. So we might place an object like a metal that's been heated up into the calorimeter, which is going to be filled with water. Heat's going to transfer from the metal to the water until they are the same temperature. So remember that they reach the same temperature equilibrium. So whatever the final temperature is for the water, so whatever this temperature is right here, it's the same for the water as it is for the metal because they're in equilibrium. So we're going to use the fact that heat loss must equal heat gain. So we are going to set those equal to one another to calculate some missing component, okay? So what I mean by setting those equal to each other, Q is heat, so heat loss equals heat gain. So then that also means that MC delta T equals MC delta T. This for the metal, this for the water. So let's do a couple of practice problems so you kind of see what I'm talking about. So we have a 230 gram sample of lead, it gives us specific heat, and it's heated to 58 degrees. It's placed in a calorimeter of water at 22. So let me kind of draw this for you real quick. so you can kind of get an idea of what this would look like. So this is a 230 gram sample of lead, and I've heated it up to 58 degrees Celsius. And I'm going to put it inside a calorimeter that has some unknown mass of water. That's what I'm trying to determine. But initially it's at 22 degrees Celsius. So I put the lead down in here. The lead is 58 degrees, while the water is 22. So we know heat's going to flow from the metal to the water until the final temperature is 30 degrees. So we know that heat lost by the lead has to equal the heat gained by the water. Now, I put these signs, negative and positive. Negative just means heat lost. Positive means heat gained. I'm going to show you an example of when it's essential that you include those negatives and positives, because technically when heat is lost, the final temperature minus the initial temperature is going to give you a negative number. So then what this negative does is they cancel those out. Okay? If you just do delta T as always a positive number, then you won't have to worry about your signs, except in an example problem I'm going to show you. So it's kind of up to you. I think it's good practice to just always put them in there. Doesn't really matter. Okay, so what that means is that MC delta T for the lead has to equal MC delta T for the water. So for the lead, the mass is 230. Specific heat is 0.1276. And the change in temperature, it went from 22 to 30, so that's 8 degrees Celsius. Oh, I'm sorry. I was looking at the water. Lead went from 58 to 22, so it is 28 degrees Celsius. Now I'm going to set that equal to, I don't know the mass of water, that's what I'm trying to find. I do know the specific heat of water is 4.18. That's just kind of one that you need to memorize. Liquid water is always 4.18. And then water was my 8 degrees. It went from 30 to 22. So now, if we think about it, the lead went from 58 to 20, or 58 to 30. So final minus initial, that's where we get negative 28. But then, of course, this negative and this negative make this whole side now positive. So I'm going to multiply the left-hand side together. Whoops. Keep looking at the wrong question on my work. 821.7 equals 33.4 times the mass. And then I just solve for M equals 24.6 grams. So I just set MC delta T equal to MC delta T and solved for my missing variable. All right, if you want to pause and try this one on your own, that would be a good idea. And then you can resume and make sure you got it correct. So we have a piece of metal that is in boiling water. So if it's in boiling water, remember, things are going to be the same temperature when they're touching each other. So then that means it's 100 degrees Celsius. So the metal is 100 degrees Celsius. It's put in water, and the final temperature is 28.5 degrees. So the heat lost by the metal has to equal heat gained by the water. So MC delta T of the metal equals MC delta T of the water. This one has the heat loss, so it has the negative out front. So 59.7 grams times the specific heat. We don't know. That's what we're solving for. Then we do know that the temperature went from 100 to 28.5. So the final temperature, 28.5, minus the initial temperature, 100, is 71.5. And I'm going to set that equal to the mass of water. Something else to keep in mind, 1 milliliter of water equals 1 gram of water. So if you're ever given milliliters, because you know it's a little bit more common to do volume of water, if you're ever given milliliters, it's the same thing as grams, so just don't get confused by that. So we have 60 grams of water times the specific heat of water times water went from 22 to 28.5, so 6.5 degrees Celsius. So I multiply the negatives, get rid of one another. I get 4268.5 times the specific heat equals 1630.2. I divide and get the specific heat of that metal that we used is 0.382 joules per gram degrees Celsius. All right, so in this last example of this type of problem, here is one where using your negatives is imperative because we're actually going to solve for the final temperature. So these are not hard, they're just algebraically lengthy, okay? So we have silver at 350 mixed with water at 30. So heat is being lost by the silver and it's being gained by the water. So MC delta T of silver equals MC delta T of water. So 20 grams of silver times the specific heat is 0.24. Now I don't know my final temperature, so I actually cannot plug in delta T. Instead, I have to use final minus initial. So I don't know my final, but I do know that my initial is 350. Now I'm going to set that equal to, I have 200 grams of water, specific heat is 4.18, and then I don't know the final temperature, but I know it was initially at 30 degrees. So now what I'm going to do is I'm going to multiply these two numbers together. And I get negative 4.8, so negative 20 times 0.24 is negative 4.8. Now remember, when we have algebra, to distribute to both of these. So we have negative 4.8 times the final temperature, and then negative 4.8 times negative 350 gives me a positive 1680. Again, this is not complicated. It's just some kind of lengthy algebra. So now I'm going to multiply these two together, and I get 836. So then I got to distribute that. So I get 836 TF minus 25080. So all I did was multiply everything out that I could. Now I got to combine like terms. I like positive numbers, so I'm always going to like add things to the side that makes them positive. So I'm going to do plus 4.8 TF. And then I'm going to do plus 25080 plus 25080. So that leaves me with 26760 equals 840.8 times TF. So again, I just combined like terms. So I combine these together and I combine these together. When I solve for final temperature, I get 31.8 degrees Celsius. That is the most difficult calorimeter problem like that. And again, not difficult. It's just a little bit of messy algebra. That's it. Okay. So what if instead of using just that simple styrofoam coffee cup calorimeter, we use an actual calorimeter called a bomb calorimeter. So it's used to measure energy produced by reactions that yield large amounts of heat. So typically here we're not dealing with like putting a piece of metal down in the water. We're actually doing a chemical reaction and seeing how much energy is lost or gained in that reaction. Something really important to keep in mind when we're using a bomb calorimeter is that the calorimeter itself has its own heat capacity. So when we're doing the simple styrofoam coffee cup, we just assume that it's good, it's well insulated and no heat goes into the styrofoam. But in a bomb calorimeter, it's made out of metal, and so the calorimeter itself has its own heat capacity, and so we have to account for that. So what that means whenever we're doing a reaction inside the bomb, and if it releases heat, then the heat is gained by both the water and the calorimeter itself. So the heat lost equals both of these things combined. So we just have two parts on one side. So here's an example. When 3.12 grams of glucose is burned in a bomb calorimeter, the temperature of the calorimeter increases. So this is both the water and the calorimeter. Remember, the water's in the calorimeter, they're in equilibrium. The calorimeter contains 775 grams of water, and then it gives us the actual heat capacity of the bomb itself. So it asks how much heat was produced by the combustion of the glucose sample. So because this just asked us for the heat produced, we're actually not going to need to worry about how much glucose we have, because we're just seeing how much that total amount of glucose produced. So because the temperature of the calorimeter went from 23.8 to 35.6 degrees, then the heat lost by the glucose is equal to the heat gained. And remember, it's gained by the water and by the bomb calorimeter itself. So we're going to do two parts here. We're going to do MC delta T of the water, and then we're going to add that to the heat capacity times the change in temperature. So remember, heat capacity is in joules per degree Celsius. So we don't have to worry about mass there. So the mass of water is 775 grams. Specific heat of water is 4.18. And the temperature went from 23.8 to 35.6, which is 11.8. Now we got to add that to 893 times it also, the temperature change was 11.8. So the temperature change is the same. This is the heat capacity of the calorimeter. This is the specific heat of water, and then this is the mass of water. So I multiply and I get 382261.1 plus 10537.4 equals 4876.3.5 joules, and if we want, we could say that's 488 kilojoules. All right, we're going to do another example. Maybe pause, try this on your own, and come back. So heat lost by benzene equals the heat gained by the water and by the calorimeter. So again, this is a way for us to calculate heat by measuring temperature change. So we have mass of water, 925 milliliters. Remember, that's just the same as 925 grams. Specific heat of water is 4.18. The temperature increased by 8.39. But then I have to add some of the heat is going to be absorbed by the calorimeter, which has a capacity of 784, and it also changed 8.39 degrees. So when I multiply, I get 32439.9 plus 6577.8. I add those together, 39017.7 joules, or 390 kilojoules. Okay, so both of those were just asking us to calculate how much heat was lost by the benzene, and it was 390 kilojoules. Now, if the answer choice gave you negative 390 kilojoules, that negative is just telling me that it was heat lost, but it's not necessary unless it asks you to give a sign indicating direction. Now, this question looks very similar, but we need to note that it's asking us for something different. Instead of asking us for just heat, it's asking us for heat of combustion in kilojoules per mole. So notice now, heat, if it was just the heat, it would just be in kilojoules. But because it's the heat of combustion, it's of an actual reaction. So it's how much heat is released per mole. So now the amount matters, because if it was 0.5 grams of naphthalene, it's going to be a certain amount of moles, and so we can figure out how many kilojoules is released per mole of that substance. So we're going to go about it the same way. So heat lost is equal to the heat gained by the water plus the heat gained by the calorimeter. So I have 650 grams of water times 4.18 times the temperature change, which is 6.4. And then for my calorimeter, I have 420 times 6.4. When I add all of that together, I get 20076.8 joules. This one's kilojoules per mole, so I'm going to go ahead and convert that to 20.08 kilojoules. So half a gram released 20.8 kilojoules. Question says, how many kilojoules per mole? So I need to take this grams, and I got to convert it to moles. So half a gram is equal to 0.0039 moles. How do I get kilojoules per mole from kilojoules and moles? We're going to divide. And I get 5136 kilojoules per mole. And this is the heat of combustion. So we're going to put a negative because the reaction releases 5,136 kilojoules per mole of naphthalene. And because this is a change in energy, so like how much energy is released or absorbed, we're going to use the negative to indicate that this is an exothermic reaction. And we're going to talk more about change in heat, which is something called enthalpy, in our next lesson. So here is a similar question, except this time it wants us to calculate the calorimeter constant, which is just the same thing as the capacity. So this time they give us the heat of combustion with our other information. So we know that on one side we have the heat of combustion. It's got to be the heat gained by the water plus the heat gained by the calorimeter. That's going to be joules, they gave us this in kilojoules per mole. This is going to equal joules, and we're going to have to divide it by moles. Okay, so because this side is in joules, I'm going to convert this to joules. So negative 3.22700 joules per mole is equal to mass of water times specific heat times the temperature change, plus we don't know the capacity of the calorimeter. That's what we're trying to figure out, but we do know it changed by 8.32 degrees. And then my question told me how many kilojoules were released per mole. So if I have 1.890 grams, I can figure out how many moles that is. So I have 0.0155 moles. So I know when I divide however much heat this much benzoic acid released by how many moles there were, I get how many joules per mole. So I'm going to multiply 0.0155 times the joules per mole, and I get 50018.5 equals, I'm going to multiply all this together, plus 8.32 times the calorimeter capacity. I'm solving for the calorimeter capacity. And I get 2,250 joules per degree Celsius. So that's how many joules per degree Celsius change the calorimeter absorbs. So these aren't difficult. They're really just algebra, but you got to figure out where to plug in what. So regular calorimetry, just MC delta T equals MC delta T. Bomb calorimetry, we also have to include not just the heat absorbed by the solution, but also the heat absorbed by the calorimeter. So up until this point, we have been talking about in calorimetry, like putting a object such as a metal into the calorimeter to look at the temperature change, or like combusting something in the previous examples. This time we're going to specifically talk about forming a solution and how the formation of a solution can be either endothermic or exothermic. And this is actually what we use in instant hot packs and cold packs. So you'll notice in like an instant hot or cold pack, it'll say something about squeezing it together. What you're doing is you are breaking some seal that combines the solute and the solvent. And when that solution forms in a hot pack, it is an exothermic solution process. And so it makes this whole pack feel hot. And in a cold pack, we have an endothermic solution, so it pulls heat from the surroundings, which makes the whole pack feel cold. And this is a little difficult for students to visualize. For the hot pack, it makes sense because it's dissolving, it's releasing heat, and it feels hot. For the cold pack, absorbing heat, you're like, oh, it should feel hot. But no, if it's absorbing heat from its surroundings, then the surroundings themselves are going to feel cold. So we're going to do a couple problems with this that are specifically solutions. Okay, so what we have here is an experimental setup that would be similar to what we would do in class. So we have a calorimeter, we have 100 milliliters of water, and it has an initial temperature of 25. We add in 5.05 grams of potassium nitrate. We stir it. And if you look, the final temperature is 21.7. So what that means is as the solution occurs, the temperature dropped. So it must be taking in energy from the surroundings. So it has to be endothermic. So it's an endothermic reaction. So it's asking us to use this information to determine what is the molar heat of solution of potassium nitrate. So what this experiment told me is how much, or will allow me to calculate, is how much heat 5.05 grams of potassium nitrate absorbed. But then we can take that and figure out how much it does per mole. So I know that my water was 100 milliliters, which is 100 grams, times the specific heat is 4.18, and the temperature changed by 3.3 degrees. So I'm using that information to calculate how much heat was absorbed by water, and that equals 1379.4 joules. Now, if that's how much heat was absorbed by the water, was lost by the water, it's also how much heat the solution process absorbed. So because this asks me for the answer in kilojoules per mole, I'm going to change this to 1.379 kilojoules. And now that's how many kilojoules per 5.05 grams, but this wants to know how many kilojoules per mole. So I'm going to take this 5.05 grams, and I'm going to convert to moles by dividing by the molar mass. I get 0.05 moles. So I'm going to divide this by 0.05 moles, and I get 27.9 kilojoules per mole. So what that tells me is that anytime I dissolve potassium nitrate in water, it's going to absorb 27.9 kilojoules per mole. This is positive because it is endothermic. Now, in this last example, and I'm sorry that these notes were so long, but it's been so long since you've had to do them that I just had to, talk for a long time. Okay, so in this example, we're dealing with sodium hydroxide. The temperature rose by 10 degrees Celsius. So if it rose, then the solution process of dissolving sodium hydroxide is exothermic. So we are going to see, okay, well, how much heat did it put out into the water? And we're going to figure that out by doing 100 grams of water times the specific heat times the change in temperature was 10 degrees Celsius. So that gives me 4,180 joules. And ask me for the heat of solution in kilojoules per mole. So I'm going to change this to 4.18 kilojoules. Now that 4.18 kilojoules is how much was released by 4 grams. I want to know how much it is per mole. So I'm doing 4 grams. 1 mole is 40 grams. So I have 0.1 moles. So 4.18 kilojoules divided by 0.1 mole equals 41.8 kilojoules per mole. This is an exothermic process, so the change in solution is negative 41.8 because the heat is released. All right, that's it. You're going to have some practice